organizers for this invitation. I changed a little bit the title. This one is more precise. So what I'm going to say is kind of follow-up of what I said in Paraty last year. But of course, not all of you were there, so this is going to be self-contained. We investigated non-locality in both multipartite systems and bipartite systems with higher dimensions than 2. Well, the most usual way to quantify non-locality, to assess non-locality, if you don't like saying quantify, is to look at the algebraic extent of the violation, right? So you simply say, if you have a Bell inequality, you simply say that rho is more non-local than sigma if this is the case, and both are above the classical limit. This is okay, and this is of course meaningful. There are some, for example, some task-based measures of non-locality for which you show that there is a trivial dependence on the task you want to perform and the extent of the Bell violation. So I'm not saying that this is not meaningful, but this is not the only way as well. For example, by using this criteria, to simply, if you violate more the inequality, you have a more non-local state, you get some weird conclusions. So for example, in this paper, which is not easy, not new, they found that if you investigate the non-locality of 2 qtrits, you get a kind of anomaly, because the maximally entangled state is not the state that maximally violates some tight Bell inequality, in this case the CGLMP. So what they found is that, of course, if you have gamma equals to 1, this is the maximally entangled state. And then they showed that if gamma is this number, you have a larger violation. So this was kind of unexpected, because although we know that non-locality and entanglement are different resources, they are as well very related. So this became known as an anomaly of non-locality. And this is not an accident. It happens consistently for all these dimensions. So if you look at the extent of the numeric violation for the maximally entangled state, you get this column. And for some state that is not maximally entangled, you get these numbers. And the difference between the maximally violating state and the maximally entangled state grows with a dimension, right? So you have this kind of anomaly for all dimensions. Okay, this is if you consider directly the extent of violation, right? But there is an alternative reasoning that you can do, which is more or less as follows. Well, first of all, any violation means that you need that you cannot describe your results with a local model, right? So it doesn't matter if you violated CH as h by 2.01 or 2.2. In both cases, there is no local model that is capable to describe the results. On the other hand, non-local hidden variable models are needed whenever you have a violation, no matter the extent. If you have a violation of 2.01, you need a non-local model, right? So in this sense, you may think that given a state and a set of fixed parameters in your experiment, the situation is either local or non-local without gradations for fixed stuff, right? Because of this kind of Boolean thing you get, need or don't need a non-local model. So following this thinking and inspired by the anomaly, we defined a candidate to quantifier of non-locality as a volume as follows. You take all, well, this is an initial definition. In the middle of the talk, I will give you a more general and powerful definition, but I'll stick to this one as a start. So, for example, imagine you have the CH-SH scenario. Then you have 2 observables per party. And then you make all possible variations in these observables. And every time you get a violation, you give weight 1. And if you don't, you simply give it 0 weight. So then this is an integration where this set is the set of experimental parameters that lead to violation, right? And of course, the measure of integration has to be a neutral one. There are measures in most of the case. Okay, so first thing, just apply this to the trivial case, you know, where there's no anomaly and see what you get, right? So this blue line, this red line is the entanglement, the entropy of entanglement. The blue line, the numeric violation of the CH-SH inequality above this, because I'm sorry, this is all these cubes are normalized to 1, right? So the classical bound is here, and the red, the black line is that volume that I just defined. So you don't get anything new, but it is at least consistent in this simple case, right? The maximally entangled state is the maximally non-local state, no matter if you are using the extent of violation or that volume, okay? But interestingly, when you go to that anomaly case, where you have the entanglement and the maximal numeric violation attaining the maximal values at different states, when you use the volume of violation as a quantifier, you don't get the anomaly, right? This square is this rescaled rectangle. So the maximally, if you use the volume, the maximally non-local state is the maximally entangled. There's no anomaly, right? Okay, and the more fundamental definition I told you is that, okay, why don't you, instead of integrating in the space of, for example, measurement directions in that particular Bell context, why don't you go to the space of behaviors and integrate in the space of behaviors? And we did this, in fact, in a paper that was published in 2017, and I'll show the results. So this part of the work was made in collaboration with Anna de Rosier and Wiesiu Laskowski from Gdansk and Tomasz Wertezi. And what we did was to generalize that calculations for not only for qtrits, but for dimensions like t equals to 7 or even more. And we did both. We integrated in a particular Bell scenario, like I showed you, and we integrate in the whole space of behaviors. Well, hopefully this paper will appear in Physical Review A soon. Okay, so this is this is the dimension of the qudit, right? So here you have a qubit, qtrit up to 7, and this is the, of course, that volume you can normalize so that it becomes a probability of violation when you randomly pick some observables. So you don't see any anomaly, and but note that the probabilities are quite low, and this is a logarithmic scale here. So this is an exponential decay. So this is more or less meets our intuition that non-classicality should vanish as we increase the dimension of the systems, right? And they found the same behavior in Gdansk. This was made via Monte Carlo and this SDP, right? This is integration in that space I told you, and here in the space of behaviors. And also we see no anomaly, right? In fact, this is not updated. They have already for d equals to 10, and no anomaly showed up. But the probabilities are much higher, you see, 30%, 20, 15%. But we don't have anomaly in both calculations. I will argue that this definition in the space of behavior is more fundamental, although it is probably impossible to access the whole information that you have there in a single experimental setup, while here you do get information for a single experiment. Okay, no anomaly in both approaches. Then we set to investigate a case that turned out to be interesting. Okay, you go to dimension D, but you use states that do not have full rank, right? And then, like this one. In fact, we investigated this state, but we have a dimension 4, right? So again, this is our results in a particular Bell context. And what we found is that, okay, this is not exactly an anomaly, because you cannot say that this state, the maximally symmetric state containing only these 3 cats, is maximally entangled, because this is missing. But in any case, the maximally symmetric state, which is here, is not the one that maximally violates the inequality, right? The state that maximally violates the inequality are those 2 which are given by this. So you can call it a weak anomaly. When you go to the space of behaviors, it disappears. The maximally symmetric state is the state that maximally violates the inequality, that has the largest volume. And so we can understand this well, if you here you consider all relevant Bell inequalities. And here you consider a single Bell inequality, a tight one, but single. If you have low dimension, this is not very serious because, for example, in the simplest scenario, you only have one. So the two approaches are equivalent. But as soon as you increase the dimension by choosing a single Bell inequality, you are giving a bias to your procedure, right? Okay, this is all numerics. The only analytical thing is the definition. But very recently, Lipinska, Kochod, Alejandro Matar, and Tony Assim on several properties of this proposed measure analytically, and they are nice properties. For example, the probability or the volume is invariant under local unitaries, and it is only zero. It is zero if and only if the state is separable. And this one is interesting because we noticed this numerically, and they were able to show analytically. Whenever the number of measurements grows in both parts, for Alice and Bob, the probability of getting a non-local behavior goes to 1, right? And they showed that that there is no anomaly for full correlations inequalities. So the result is not valid in general, but you must have full correlation inequalities, bipartite case, but any number of observables and outcomes, right? So they were able to show that whenever the state is more entangled, then it will have a larger volume. So they have shown that the volume of violation is a monotone of entanglement in this case, right? So of course there will be no anomaly. But we have to be careful here because we are not trying to convince you that this is always the case in general, right? What I do believe that it is true is that maximal entanglement and maximal non-locality should coincide. But I will give you an example that this monotone dependence should not hold in general. So this is a family of qtrits. That one is the maximally entangled state. Sorry, I'm not showing the state, but it's just to illustrate that here we have the maximally entangled state and the state with maximal probability. Okay, no anomaly. But if you look at this region, you see a non-monotonic dependence involving the non-locality, and entanglement is like this, right? So it grows with alpha while the non-locality presents some strange behavior. Okay, it was about a pair of qudits. Now we have also investigated 4, 5, 6 qudits, right? And well, the rest of the talk I will read line by line. Okay, now I've selected some results to show. So there is a single analytical result on this volume is that the volume of violation, the probability of the violation for the singlet state in the CH-SH scenario is this number, 2 times pi minus 3, right? So what we showed, it is easy, is if any state it means that it is genuine tripartite in the case of 3 qubits, right? So this volume of violation be seen also as a witness for multipartite entanglement. And also it has some interesting non-additive properties. So if you get two, this is just notation, it's two singlets, okay? If you take two singlets and calculate the probability of the tensor product of these two singlets, you get 1.7 the probability of violation, this one, okay? So there is no additive property, but it's an interesting multiplicative property because classical, not that this is not local. There should be 1 minus this. So this is a kind of multiplicative feature, and we numerically found the same number, right? So the tables, the piece of tables that I'm going to show, we have the state, the settings, and here the statistics and the probability of violation. So 4 qubits, you have GHZ state, the probability of violation grows a little when one of the parties is able to do more than 2 measurements, and the same for W states, and as expected, the probability for GHZ states is larger than for W states. But then something strange happens, at least for me. The GHZ state is not the state that presents higher probability. For example, cluster states have a larger probability to violate local realism in comparison to GHZ. So this was surprising enough, but if you consider random states, you get, now this is 5 qubits, right? There was 4 qubits, now 5 qubits. So a GHZ state has a probability 99.6% to present local behavior whenever each part can make 2 measurements only. If you pick any old random state, the probability is higher. So this was very non-intuitive, but after thinking a little, I think that this is due to the rank. The rank, the GHZ state is 2. Pure, yeah. So in a way, the GHZ state in a lot of directions in the space, in Hilbert space, and then when you increase the number of qubits involved, this starts to become serious. So the random states, in a way, they feel a larger part of the Hilbert space. But in any case, it's a very counterintuitive result. So the fact is, all typical states of 5 or more qubits violate local realism almost with certainty. And also, the probability of violation saturates fast to 1 when you increase the number of observables. In this case, I am fixing the number of observables of all parts but 1, and here is the number of observables for this part, right? So it seems that that theorem that Tony's group has shown that when you increase the number of observables, you get probability 1 in the case of 2 qudits, is also valid in the case of n qubits when n grows. This is just the same information. I'll not comment on this. Also, we investigated the probability, yes, the probability of violation of bound entangled state. And so this is a 4 qubits Smalling state, and the probability is very low, but it grows exponentially when you increase the number of observables per party. As a way to detect bound entanglement, right? Because note that we don't have to know, we don't have to search a particular Bell inequality for detecting the locality state. You just go to the space of behaviors. Okay, I think that's it. Thank you.